record locally, por favor. Don't crash. I think we're in good shape. Okay, yeah, so a few things to get started. First, I am like out of paper, out of markers, out of pens. It's getting a little rough. I got 3 sheets of paper to play with on the dot cam, but unfortunately they're all one-sided because it's all like old homework of mine from grad school. So today's lecture is going to be as writing efficient as possible. So please take notes of what I say, not just what I write. I know it's kind of annoying, but today, just for today, because I finally got paid, so I'll be able to go out and buy markers and pens and all that good stuff. A few things verbally that you may want to write down. The homework for this week, I apologize. I originally scheduled that for one of my other classes. I scheduled that on accident to my Calc 2 class. And thankfully, one of you was kind enough to email me and say, hey, I can't see the homework. So yeah, that's why. And now you should. So it's up there, and it's just a few questions on parametric curves, all the stuff that we've been talking about. I want to play around a little bit more with parametric curves today, look at a few other kind of classic famous examples, the big one being the cycloid. And really that's it. This week is a fairly light week for us. Other news, exam 3, graded, scores are in, everything should be there. And this morning I was able to finish scanning and uploading all of my comments. So if you go to the gradebook, look under exam 3, you should see your score there now. When you click on it, you should see a comments box. And in that comments box, you'll see a couple things. Like when I first put the scores in, I made a little note there saying I will update this later once I have the things scanned. Now that the things are all scanned, I went back through and updated all of them. So if you take that URL that's in there and you paste that into your address bar, or if you can click on the link, click the link, whatever, that will take you to a CAM scanner document of the scanned page on which I wrote the things I would normally write on your paper test. The notes are a little bit more thorough than they would be on a paper test because I can't like draw arrows and point to stuff. But it should have all the same information you would normally expect to see in comments or whatnot on one of our written tests. So everything should be back and returned to you. I believe there are 2 exceptions. Maybe 2.5 exceptions. There were 3 folks who sent me either only part of the free response work, so either like sent me the first few problems or the last few problems, like a page was lost or something like that. And I've contacted I think 2 of those folks, or attempted to contact 2 of those folks to straighten it out. But if you don't have a grade in there, or if you don't have scanned uploaded feedback from me in there, that means something went wrong. Either I didn't receive from you what I was expecting to receive, or I received something that was incomplete. And that means you need to reach out to me. You need to reach out to me ASAP, and we'll figure something out. If you didn't write down the work as you did it, or you lost it, or something like that, then probably what we'll do is end up just letting the WebAssign score stand. But know that that won't fly on the final. On the final, I must have written thorough solutions for every single problem. Otherwise, it's all going to be zeros. Really don't want that. But this round, if something went wrong like that, we'll figure it out. It will be okay. What other things? There were a few issues that are the sort of thing that make my cheating senses tingle. I am not the sort of person to cast those stones, and I really hate dealing with academic misconduct stuff, so usually I do my best to not look the other way, but come up with workarounds like retests or something like that. Not doing any of that this round, but just know that the reason I have you upload your work, one of the reasons I have you upload your work, right? The main reason is so that I can give you partial credit, because online exams are ruthless when it comes to partial credit. There is none, right? And I want to be able to give you partial credit for your good work, even if it doesn't lead to the correct answer. The other one is so I can check and see that your work matches up with your answers, right? This is important for the obvious reason. I know, and you know, we all know, that we live in 2020, and 100% honesty is not always the most rewarding path for everybody. But in mathematics, it is. In mathematics, the only path to any sort of reward is 100% honesty. And so if I made a remark like, this looks a little bit strange, or this work doesn't seem to lead to your answer, or if I was even more verbose about it, just know that's the sort of thing that I am going to have to be very strict about on the final. The main purpose of the final exam is to make sure that you guys have the skills and tools that you're going to need to succeed in the next class. And so there really isn't room for me to wiggle or be soft about that stuff there. If I do that, then I would be doing a disservice to either myself, and if I have you as a Calc 1 student, or whomever is teaching your next math class. And the idea is not to be ruthless towards you or mean towards you or anything like that. I want everybody here to get an awesome grade and to feel really good about this class. And the way to make that happen is not to use outside resources or do anything shady at all. It's just to talk with me and to work with me and to put in the time and to practice. And I trust that that's what everybody is doing. I trust that everybody at their heart is working as hard as they can and is going to do well here. But what I need from you guys in order for me to feel comfortable with my professional ethics is to make sure that on the final exam especially, that you give me thorough written solutions to every single problem that you answer in WebAssign. That way I can go through and give you, first, all the partial credit that you deserve, and second, I can trust that the grade that I'm assigning is a legitimate representation of your skills. It's important. It's important on a deep philosophical level to me personally. It's important regarding yours and my professional ethics, and it's important for your success in the next class. So I'll leave it at that. Please, when you take the final, which will be run very similarly in WebAssign, make sure that you are writing full, thorough solutions to every single problem, and that you scan those and upload them and get them all to me so I can grade everything and everything can go as well as it possibly can. To those of you who do not see your grade or anything like that missing in WebAssign, please contact me right away. Send me a Canvas message or even just hang out here for a second after class so we can chat. I think there was one person from whom I either did not receive or cannot find the scans of their written work. And then there were a couple of people who sent me partial scans or something like that. So reach out to me as soon as you can. Let's get that fixed. Let's get those grades. And the grades were very good, which is nice. You know, this was what I would expect with an online test. It was fairly gentle. And so I'm proud of you guys. I hope you guys are all happy too. And if there are any questions about exam 3, let's get those out of the way now. So does anybody have any questions about the feedback system or the grading or anything at all having to do with exam 3?
Will you be opening exam 3 back up?
I can open it for review, I believe. Is it the case that you cannot get in there and review it right now? I'm not sure what it looks like from your end.
Let me, I can look at it in WebAssign. It just says assignment cannot be loaded. It says it's password protected. For more information, go home.
I see. Let me see what I can do about that.
Okay.
So, 3, schedule edit restrictions. So can I lift the password restriction after a certain time? Yeah, drop security restrictions after, I'll set it to drop security restrictions after yesterday. Or what was the date of the exam? It was Thursday? Tuesday before last, is that right? I'll just set it to drop the security restrictions yesterday. That way you guys will be able to get in.
I think it was the 9th.
It's the 9th? Thursday
I
before
think.
last? Oh, just last Thursday?
That was the last Thursday. I'm really not sure because days don't matter anymore.
I feel ya. I'm in the same position. All right, well, here's what I did. So I set the security restrictions to drop after the 10th. Oh, I need a time. All right, 11:59 p.m. All right. So you should be able to get in there without a password now. Let me know if you encounter any other troubles as you go back and review. So there should not be, but if you do encounter any such things, let's see, maybe, yeah.
Let me in.
Should be good now, okay.
Yep.
So Sweet. All right.
Perfect.
Beautiful. Is there a date for exam 4 yet? Yeah, exam 4 is going to be a take-home test. So I will give you exam 4. I'll distribute it electronically on the last day of class, which for us is next Thursday, the 23rd of April. So it's going to be like a little project, like a little, think of it like a take-home test. You're intended to work it on your own, but it is open note, open book. No internet though, no internet, just notes and book. And then you will hand it in to me electronically. It will be a Canvas Dropbox thing, just like we did for the free response work for exam 3. And that will be due on the day of the final. So the final exam for you guys, is the 30th at 1 p.m. So that is when I'll have your take-home test, which is what exam 4 will be. Exam 4, the take-home, will be due in Canvas on the 30th at 1 p.m. So you'll do it just like you did for the free response, like partial credit scratch work thing for exam 3. I will send out a PDF for exam 4. You can print it and write on it if you want to, or you can just write answers on a separate sheet of paper, and then you'll scan those using your scanner app on your phone and upload them to Canvas. As long as you get that uploaded before 1 p.m. on the 30th, the day of the final, I will take it, and that'll be it. Yeah, so exam 4 is going to be given out next Thursday, and it will be due, what's the day of the week? Exactly 1 week after then. Any other questions regarding like test stuff? Feeling good? Okay. So, like I said, I'm very resource limited right now. So I'm going to be writing a little bit small and as little as possible. There's a couple big examples I got today. And they're all just graphing parametric curves. So let's sketch the curve. X of t equals 3 cosine t, and y of t equals just sine t, where 0 is less than or equal to t is less than or equal to 2 pi. Okay. So this is the first example I'd like to work. We know if that 3 wasn't there, if this was just cosine t for x and sine t for y, then I would be sketching the unit circle. That's one of the examples we looked at last time. But with that 3 there, we have to ask ourselves what changes. So this is something like the unit circle, except it's been modified in some way. I'm going to go ahead and move through, Antoine, because we've got some background noise coming in there. But you can unmute yourself if you want to talk or ask a question or anything just by holding down the space bar or clicking unmute. So the question is, what does this 3 do to the parametric curve? So we know that x equals cos t, y equals sine t gives the unit circle. We know that, or we can deduce from that, that x equals r cos t, y equals r sine t gives the circle of radius r. In fact, one of your homework problems is something very much like that. And it's not at all hard to show. This is washed up really bad. But here, I've kind of changed the radius, if you want to think of it that way, of just one of these guys. I've made the x's now go from -3 to 3, and the y's still go from -1 to 1. And so if you think about that, if you picture a circle and you stretch it out horizontally, what you get is an ellipse. And so I have every reason to believe that our curve here is an ellipse. If I wanted to, I could start making a table, and maybe in order to save some space here, is there a way for me to make that table in the screen share? No, it's okay. We'll do it like this. So I'll have my t values here, my x values here, and my y values here.
A quick question. Are you in a section of the book?
Yes, I think in your textbook, this is section 8.4, maybe 8.5. Let me double check. Yeah, 8.4.
Thank you.
So my t values, my times here are running from 0 to 2 pi. So I'll just input some kind of natural choices between 0 and 2 pi. Chop it up into quarters, say. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. When t is equal to 0, what is x? What is the x coordinate of the initial point along this parametric curve? Yeah, right, cos of 0 is 1, so 3 times the cos of 0 is 3. And y of 0, if I plug in t equals 0 to this function, I get 0. So the initial point for this parametric curve, if you want to think of it as a little ant walking around on the page, is 3, 0. When t is pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. When t is equal to pi, cosine of pi is -1, so x will be -3. Sine of pi is 0. When t is equal to 3 pi over 2, cos of 3 pi over 2 is 0, so x is 0. And the sine of 3 pi over 2 is -1. And then when t is 2 pi, the cos of 2 pi is the same as the cos of 0, so x is 3 times 1, which is 3. And sine of 2 pi is 0 again. So my graph, and I encourage you to do it like I am, plotting the points in time order so you can think about it as a moving particle or as a little ant walking around the page. So this is 1, this is -1, this is 1, 2, 3, this is -3, -2, -1. My starting point, my initial point is 3, 0. So right here is where I begin. And then if I think about these functions as functions of time, sine of t for t values close to 0, as t increases a little bit, sine of t starts off increasing. So I expect my y values are going to start going up, and cosine of t is a decreasing function when you start off. Near 0, cosine starts off going down, sine starts off going up. So I expect my curve is going to start off going something like this, with the x values coming in and the y values going up. The next point that I know is on the curve is 0, 1. That's right here. So what's happening is something, sorry, forgive me, mark 1 up here. 0, 1. We're going to go up to there. I'll bring this down here a little bit too. The next point that I know is on my curve when t is equal to pi is -3, 0. So this is the point associated with t equals 0. This is the point associated with t equals pi over 2. And over here would be the point associated with t equals pi. And you can see what's going to happen. The next point I have is 0, -1. So we're going to come over here. And then the next point I have is 3, 0. So we're going to come back over to where we started here. So my little ant is walking around this ellipse in the plane. Like this. So this is the graph of the parametric equations x equals 3 cos t, y equals sine t, where t runs from 0 to 2 pi. It's an ellipse whose semi-major axis is parallel to the x-axis, actually runs along the x-axis, and whose semi-minor axis runs along the y-axis. We got it. We can get this two different ways, making the table or through this little discussion here. So we could have actually expanded this little discussion and neglected the table altogether if we were very careful. I know that these x values run from -3 to 3, and these y values run from -1 to 1. So I could have known that my curve's minimal x value would have been over here at -3, and its maximal x value would have been over here at +3. I know that cos t, comma sine t, or x equals cos t, y equals sine t would be the unit circle, so I expect it to be unit circle E, just stretched out in the x direction. And that's exactly what we got. But it never hurts to make a little table like this and to be a little bit more careful. Questions about this one? A fun question I'd like to ask is, could you have, and I'm going to try to save on paper here, so I'll ask you to write this down, but I need to save paper, so I'm not going to write it down. Could you have eliminated the parameter and found the Cartesian equation for this ellipse? So what is the regular Cartesian equation for this ellipse? I would start by squaring x and squaring y and adding them just like we did to try and eliminate the parameter in the unit circle problem. But what you're going to find is that things don't come out quite as nice. And so you're going to end up having to be a little bit more careful. It's not x squared itself that is going to add to y squared to be 1. I might as well, I guess I'll go ahead and take a look at this here. So in answering this question, we're going to return to that old chestnut. Sine squared t plus cos squared t equals 1. Now sine squared, that's y squared. But cos squared here is not just x squared, it's x over 3 squared. Do you all see that? Because x is 3 cos t, x over 3 is cos t. So cos squared t is x over 3 all squared. So it's this which is equal to 1. And now this is starting to look like the Cartesian equation for an ellipse. That's the same as saying y squared plus x squared over 9 equals 1. And you may remember that the general equation for an ellipse is like y squared over b squared plus x squared over a squared equals 1. This is the equation for an ellipse whose semi-major axis, depends on who's larger, b or a, but whose vertical axis has extreme values b, and whose horizontal axis has extreme values a. So from this, with an appropriate background in conic sections, which maybe you got in high school and maybe you didn't, we would have known that these parametric equations would give this ellipse. So again, it's eliminating the parameter. All right. So any questions about this example? How we got that graph, or how we could have anticipated what that graph looked like? What would happen? Oh yeah, go ahead, please.
Can you always eliminate a parameter?
That's a good question. I know the answer is in theory, yes, right? So I know that there's a theorem from real analysis called the implicit function theorem, which says any curve, as long as it's not at that point vertical, can be locally expressed where y is a function of x or x is a function of y. The practice, though, actually doing it algebraically, I don't think so. I think it's not too hard to come up with a set of parametric equations where you could not eliminate the parameter just because the algebra would be nasty. Now, that doesn't mean that it's impossible in the mathematical sense. It just means that whatever the algebra steps are that would take you there are not the sort of thing that we can write down using the notation and systems that we have. So theoretically, yes. In practice, it depends on your algebra skills, really. So whether or not the parameter can be eliminated is a tricky question to answer well. And I think the sense in which you're asking the question, its answer is no. Because there are algebra equations that we cannot solve, right? There are algebra equations that there are not nice ways to write down the solutions to. Like 2 to the x equals ln of x. That's an equation that has a solution. It actually has 2 solutions. It's not too hard to see them if you graph them. But you cannot, there's no algebra step that will solve that equation for x. And in the same sense, I could write down a set of parametric equations where the algebra steps to solve for the parameter and plug it into the other either don't exist or are involving things like special functions and stuff that we don't know. Does that answer the question as you intended to ask it?
Definitely.
Okay, cool. Any other questions about this example? Comments, thoughts, concerns? Okay. So the next example that I'd like to look at with you guys is another one that kind of like this feels a little bit polar-y. To choose the right way to do this, I think we'll do it. We can do the Archimedean. So let's play the same game. Oh, and before I actually do this, I want to ask you another question about that last one. Come back to this and think about this with me for a minute. What do you think would happen if I replaced t by negative t? What if I gave you the parametric equations x equals 3 cos negative t, y equals sine negative t? What do we think that would do to this picture here?
The same thing, just go backwards.
Exactly, yeah, you hit it right on the head. So it would be like turning time to run backwards, right? Swapping t for negative t is not going to change the shape of the curve at all. It's just going to change the direction in which you walk it. So if I did that, if I asked you to graph 3 cos negative t and x equals 3 cos negative t and y equals sine negative t, the curve would be the same, but the arrows would point the other way. And that's true in general. If you swap t with negative t, you're just running the clock backwards. You're walking the same path, you're just walking it in the reverse order. So we would still start here, but then instead of starting out going up, we would start out going down, and we would walk around like this as t runs from 0 to 2 pi, instead of like this as t runs from 0 to 2 pi.
The ant analogy helps.
Yeah, I like
it because you're just getting a different direction.
Right. Yep. Yeah, exactly. And that's how most mathematicians think of this. Not necessarily as an ant, but as a particle moving, as something moving around. The analogy with time is very, very useful for these. Okay, so with that in mind, let's take a look at this guy. We could try eliminating the parameter first. That's an option. We could try making a table first. But what I'd really like to do is to start out with a sort of discussion. And here, let's let where t is allowed to run from 0 all the way out to, let's say, 4 pi. So what's the difference between this example and the unit circle example, or this example and the last example? Well, we saw that when I multiplied the x equation by 3, that stretched it out in the x direction by a factor of 3. If I had multiplied the y equation by 3 instead, that would have stretched my unit circle out in the y direction. I would have gotten an ellipse just oriented the other way, rotated 90 degrees. Here, though, I'm multiplying both of them by the same thing. So normally that would just increase the radius of the circle. But instead of multiplying by a constant, I've multiplied by a variable. So let's imagine an ant starting out thinking he's walking around the unit circle. But in addition to doing the circular motion, he thinks the circle is getting bigger as time goes on too. What kind of path is that going to trace? So I think a fun thing to do here would be to play with this in Desmos. So sorry, I know you can't see right now. I'm going to swap my screen sharing over to the browser. I'm going to input this, and remember Desmos likes these as ordered pairs. So I'll call this t cos t, comma t sine t. And I'll let x first just run from 0 to 1/2. So definitely when t is equal to 0, imagine you're making a table, right? I don't want to waste the space on the paper right now, but imagine we're making a little table. When t is equal to 0, x of t is 0 times the cos of 0, is 0 times 1 is 0. And y of t is 0 times the sine of 0, is 0 times 0. Those are both 0. So we start off here at the origin. I'll share the full screen so you can see my mouse. We start off here at the origin, because when t is 0, both x and y are 0. And then as I let t increase a little bit, we start walking out, right? Because this guy is no longer 0, forcing the x-coordinate to be 0, and sine wants to increase. So if this number in front of cosine and number in front of sine, if those were both constants, I would either get an ellipse or a circle. If they're the same constant, I would get a circle of that radius. If they were different constants, then I would get an ellipse stretched in the directions that the constant indicates. But here, since that t is a variable, it's increasing, then what's happening is I'm walking a circular type path, but the radius increases as I walk it. So if I let t increase past 0.5 to 1, to 2, to 3, to 4, to 5, to 6, you see I'm getting a spiral. If I walk all the way out to 2 pi, we've gone around the spiral once. If I walk all the way out to 4 pi, I will have done 2 loops. If I walk all the way out to 6 pi, I'll do 3 loops. 8 pi, I'll do 4 loops, and so on. This particular spiral is one that we've seen before. So we know that x equals r cos t y equals r sine t is a circle of radius r, hence our equations, x equals t cos t, y equals t sine t, should be circular, but with increasing radius as we walk, i.e., a spiral. And we're walking out at a constant speed. So this multiplier out front here, t, is like the speed at which the radius is increasing. So we end up with a spiral that goes out at a constant speed, because the rate of change for that radius, the rate of change for the function just t, is constant. It's a linear function. So there's 0 to 2 pi. And there's 0 to 4 pi. My initial point is right here. My terminal point, or my finishing point, is right here. All right, so there's my starting point and my ending point. And the orientation is like this. So you see how that's kind of like a circle whose radius is increasing at constant speed? Another way to think about this, you know, my granddad was a weird guy. As he got older, he got lazy, as many people do. And he didn't like cutting his lawn anymore. So what he would do is he would take a big stick, a real big heavy stick, and he would drive it into the ground. And then he would take his little, you know, self-propelled walk-behind lawnmower, tape down the handle that tells it, you know, I'm here, keep going, start it up, tie it to that stick, and then let it run around. And because the rope would wrap around the stick as the thing went around, it would slowly come in and cut this neat spiral pattern, and he didn't have to do shit but sit there and sip his beer. Same sort of thing is going on here, right? Only it would be going in the other direction for the lawnmower analogy. You're coming in at a constant speed, or here you're coming out at a constant speed. So it's like you're walking a circle, but your radius is increasing all the time. So if you walk around in a circle, but your radius is allowed to increase as you do that, then you'll end up walking a spiral. Do we see where this spiral picture is coming from? Do you understand the analogy with a circle whose radius is changing as you go around? I can't talk about this and not talk about something else that's ever popular in mathematics whenever lay folk like to sit down and talk about math. It seems like I can only ever go about 5 minutes without someone bringing up the golden ratio or something about sacred geometry. That special spiral that you see so much when people ramble about, you know, the golden ratio or Fibonacci numbers, is very closely approximated by a curve like this called a logarithmic spiral. So how can we make other spirals? Now, what makes a spiral a spiral? It spins around and goes out, right? So it's the x of t having cos t in it and y of t having sine t in it that does the go around, right? Because that's your circle. And then whatever you slap on out front here is what determines how fast the spiral grows out. Here, the spiral is growing out at a unit speed, at constant speed, because the rate of change for t there is 1. If I wanted something that grew a lot faster, I could try this. This is also a spiral. But it grows outward like e to the t rather than like t in our last example. I'm not going to sketch the graph here because this thing is like a circle whose radius is e to the t or whatever, a spiral whose radius is like e to the t. It grows very, very fast. I would need a large page to draw any meaningful chunk of it. But that's where our friend Desmos becomes useful again. So I'm going to walk this way in here and start looking at just the first little bit, and we'll let it expand. We'll watch it grow. All right, so you can't even really see it. Way down in here, it's the first little bit of what's going to be a very neat, very similar to the golden ratio type spiral. This tiny little red sliver that you see there is just as t goes from 0 to 0.1. If I let t go from 0 to 1, it looks like that. 0 to 2, 0 to 3. Already I need to start zooming out. 0 to 4, 0 to 5. Let's come back to about this level. 0 to 6, 0 to 7. We know that these will look nicest if I use multiples of 2 pi. So let's do 6 pi, 7 pi, and zoom way out. This is a logarithmic spiral. That's what they're called. And the spiral that you see associated with Fibonacci numbers so much, let's go all the way out to 12 pi, are very nicely approximated by these. If I wanted something that grew slower, I could use a slow growing function like ln(t). Here, of course, the natural log isn't defined at 0. I should start this at 1 and let it go first maybe to 2 or 3. So we can play with these. And I can let t grow to 3 or 4 or 5. Let's zoom in more. This will be an exceptionally slow growing spiral. And it'll get more dense as you go further and further out, because log t starts off growing reasonably quickly. Ln t starts off with a rate of change close to 1, but that graph ln t levels off as you go further and further out. So if I look at a full, a nice range of t for this, you end up getting a crazy looking spiral like this that starts off very sparse, but then becomes very, very dense as you go further out. So there's this whole family of spirals that you can get as parametric curves by taking x of t equals cos t and y of t equals sine t and multiplying both of them by any monotone increasing function. And that will yield a spiral. If you use a very fast growing function like e to the t, you'll get a spiral that blows up and gets fast really quick. If you use something that grows at like linear speed, when you multiply both of them by t, then you get the Archimedean spiral that we saw when we talked about polar coordinates. This is the same, so let me come back here. This is the same graph as the polar equation r equals theta. But the parametric setting is the nice setting to study spirals like these because you can modify them a little bit differently. And you can kind of study the X and Y coordinates separately. I think it's a nicer way to think about it in some senses, because you're not chained to this idea of walking around the circle at a particular speed. You could modify that also. Questions about either of these two examples, the ellipse or the Archimedean spiral?
I don't have a question about that, but I do have a question about, like, if you were to put, what number would affect putting spirals in different quadrants, like quadrant 1 and quadrant 3, and not in 2 and 4?
So let me flip back to Desmos. This is a good thing to play with here. Let's start with the question about the circle. Ooh, that's cool. What if I just wanted to move the unit circle to live somewhere else? Suppose I wanted to translate this whole circle to the right by 2 units. Well, that would mean I want to take every point on this circle and add 2 to its x coordinate, right? So if I add 2 to all the x coordinates, that moves that circle to the right by 2 units. If I wanted to take this circle and drag it down by 1, that means I would subtract 1 from all the y values. So moving the graphs of these parametric equations around is very, very simple. It's very, very intuitive. You do exactly what you would think you do. To move it up, add to the y's. To move it down, subtract from the y's. To move it left, subtract from the x's. To move it right, add to the x's. So if I wanted to position this circle of radius 1 somewhere over here in quadrant 3, I could subtract 2 from the x's and subtract 2 from the y's, and that would put me down there. And then the same thing will work with the spirals, right? This will actually work with any parametric curve. So if I had my Archimedean spiral, t cos t, comma, t sine t, and I graphed it from 0 to 4 pi, 0 to 4 pi, and I wanted to see how do I move this up, down, left, right, wherever. I could drag it left by subtracting 2 here, and that will move the whole thing over 2. If I want to move the whole thing way over and way down, maybe I'd subtract 15 here. Let's put it up in quadrant 2. Let's also add 15 there. All right, and that moves the whole thing left by 15 units and up by 15 units. Does that make sense?
Yeah, it does. How would you keep that spiral in quadrant 2 and put another one in quadrant 4?
I don't think I could do that with a single set of parametric equations. So
It have to be another set.
Yeah, exactly. Here what's going on is because both of these are continuous functions, t cos t minus 15 and t sine t plus 15, the graph here is going to be a continuous graph. So in order to have 2 pieces that are completely disconnected from each other, you would either need these equations to be discontinuous in that way, or you'd have to use a separate set of parametric equations.
Okay, yeah, there was a problem in the homework that it wasn't spirals, but it was just like it was in one quadrant and then it was in another quadrant and it looked like it came across. So
there are some things like that, like some lemniscates that you may have encountered when we talked about polar coordinates that are a bit like that. I would be curious to see specifically what that problem was asking for. Ooh, let me make your video a little larger here. I'm blind as a bat. Turn off the screen share, John. Let's see. So which one are we looking at?
this one right here. Like it was asking, it gives you a problem and then asks you to so you want to match the problem to the graph. And this one was confusing.
Yeah, that is a little bit confusing. So what I would do there is I would ask, let's see, they don't give you any orientation either. So, I would have to think about that for a little bit, but what I see when I look at graph 2 there, the one that you pointed at, if you draw the line y equals x over top of that, you see that that kind of runs along the line y equals x, right? He's got a kind of symmetry about that line.
Yeah.
So I suspect that whichever one of those equations also exhibits that same sort of symmetry would be the one that would work there. Sometimes we can get here by thinking about known graphs, right? Like number 50, I could tell you right away that number 50 looks a lot like y equals x, right? They're very, very similar. The only difference is that the angular velocities are off. They're both sine of something times t. So I would suspect that maybe that's number 50. But then I would also want to graph them. I would use some sort of graphing utility or try to come up with some other way of thinking about it to be a little bit more certain. It's definitely not 49. It could also be 51, right? 51 is kind of exhibiting a y equals x type symmetry. So I would play around with those, but looking at that curve right away, I don't see any way to immediately deduce what equations would give that curve. So that is intended to be a process of elimination type thing, where you say one picture at a time and you say, oh, okay, well, it couldn't be these equations because this, equations because this. And then you narrow it to one or two, and maybe graph each of those and see if you can come up with a reason to believe one or the other. But yeah, think process of elimination. Try to rule equations out based on the graph. And then once you have just one or two sets of equations left, go ahead and graph those and see which ones match.
Okay, thanks.
Yeah, of course. Okay. So the next example that I wanted to look at with you guys is called a cycloid. And these are interesting curves that we've all seen in real life. And it's so rare that you get to see a perfect geometric object in real life. Here in Gainesville, a lot of people ride bicycles. A lot of people ride bicycles at night. And that's a little bit dangerous. But I'm sure at some point when you were a little kid or here driving around watching people ride bikes at night or on a walk or on a run or whatever, you've noticed that some people put lights on their wheels. So if I had a wheel rolling along the ground, and I put a light on the wheel, then as that wheel rolls forwards, this is spinning, right? So if I look a little bit later in time, that light will have rolled up to maybe here. And if I look a little bit later in time, that light will have rolled, or that wheel will have rolled, and so that light will have moved maybe up to here, and so on. So the question becomes, what is the path that this light takes as the wheel rolls around? So maybe somewhere in here it was at the top, and then it starts coming back down, and eventually it would come back down like this. And then as the wheel continues to roll, it would continue doing something like that. So my art is bad and I feel bad, but you can get the picture. So what is this path? In other words, what is the path that a fixed point on a rotating wheel follows as the wheel rotates? So the path that a fixed point on a rolling wheel takes is called a cycloid. They're symmetric, of course. I know as I've drawn it here because I wanted to show this point, this path is going through this point, and that point it's not looking symmetric, but they're always symmetric. They might look like they're halves of ellipses, but they're not. It's its own thing. It's its own thing, and it turns out to be very nicely described in terms of parametric equations. So let's see, and here, let me get you a nice visual. Here we go. So you see this fixed point along the wheel. As the wheel rotates, the wheel's moving forwards and the point is moving up and down. So you get this sort of a path, and it looks a lot like half of an ellipse, but it's not half of an ellipse. The shape isn't right for it to be an ellipse. It's a little bit different. So what the hell is it? Well, it turns out it's its own thing called a cycloid, and we can cook up the parametric equations for it pretty nicely. Can everybody see this GIF? So you can find this on Wikipedia. Go to the Wikipedia page for cycloid. It's right there. There's also lots of others around there. Google around. Let's see if we can find parametric equations for the cycloid. So I'm going to assume that I have a wheel of radius r, and that it is rotating along the ground, and I'll think of the ground as being the x-axis. It turns out that the easiest way to come up with these equations is to think of the parameter as being theta rather than t. So instead of, well, maybe we can call it t if we want, but we're going to be using some trigonometry here. And the parameter we're going to track is the angle that the wheel has rotated. So I'm going to draw this picture a little bit after the wheel sets off. So we've been rolling for a second. The point P is the point that was originally on the ground, like right back here. When the wheel started, point P right here was on the ground. The wheel is of radius, we'll call it A, how about? So here's my center. And here's my radius. I'll call that radius A. So for the cycloid generated by a radius A wheel. And instead of tracking time, I'm going to track the rotation of the wheel. So my parameter will be theta. And so in this picture, I'm imagining that we've rotated through the angle of theta to get here. Started off, the wheel back here, theta was 0, theta increased, the wheel rolled forwards a little bit, and so we have that angle there. Inside this picture, I'm going to draw some right triangles, and we'll be able to sort out x and y in terms of theta. Here's a little right triangle. I'm also going to drop this perpendicular down here. And then I'm going to label some points. So call this point T. That's the tangent, the point where the wheel is tangent to the ground. And I'll call the center of the wheel C. Let's start with the y coordinate of the center. If the wheel is a wheel of radius A, then what is the y coordinate of the center? Oh, maybe I'll put it over here. How high up is this wheel, the center of the wheel, off the ground, if it is the center of a wheel whose radius is A?
Is it A plus 1?
Just A, right? This
A.
is the distance from the center to the edge of the circle. Wherever you look, that's the radius, right? So this distance is A, that's the same as this distance. So the y coordinate there is the radius of the wheel is A, right? It's this distance. The x coordinate is this distance, right? If I've rotated through an angle of theta, how far has the wheel rolled? That's the question. And if you think about it for a second, you'll realize that it's the same as the length of this arc that I'm shading here, because that's the part of the wheel that's rolled along the ground. And the angle that's been subtended here is theta. So the distance the wheel has rolled along the ground is the same as this distance along the curve. The whole way around the circle is 2 pi times the radius. So the little segment along this curve, this is equal to the length of the arc of the sector in the circle, radius A, with angle theta. We know that all the way around the circle is 2 pi times the radius. So if you didn't rotate all the way around the circle, you just rotated theta, that's theta times the radius. So this is A theta. Right, that is the arc length of a sector of a circle. It's the radius times the angle that you've rotated through. So the origin over here I'll call O, and this point right here I'm going to call Q. Now my goal is to find X and Y. X is the distance from O to here. This distance, this is X. I want to find the X and Y coordinates of the point P. And this distance right here, this is Y. Everybody see that? So this distance is X, is the X coordinate of the point P. And this distance right here is Y, is the Y coordinate of the point P. X, so P is equal to X comma Y. And if we get over here and start thinking about this, in terms of distances between labeled points here, what is X? Well, it's the distance from O to T minus the distance from P, the horizontal distance from P to Q. Do we see that?
Theta minus Y?
Well, let's sort it out one bit at a time. So it's the length OT, that's this whole length, minus, so I take this whole length, and to get the length X here that I want, I need to subtract this length. But this length is the same as this length, right? So the length I want here, the length X, is equal to this length minus this length. So that's OT, the length OT, minus this length right here. But this length is the same as this length. So that's OT minus PQ. Does everybody see that? It takes a little bit of thinking. It's not super obvious. But if this point right here is Q, and this point right here is P, then this distance, which I want, is this distance minus this distance. This distance minus this distance. This distance is clearly OT. This distance, by a symmetry argument, because this is a parallelogram, is the same as PQ. So the distance I want is equal to this distance minus this distance, which is OT minus PQ. And then it turns out that OT and PQ are both very easy to describe in terms of theta using geometry. OT, as I think I heard Stephanie say a second ago, that's A theta. That's the distance we've rolled so far. We observed that earlier, that the center has x coordinate A theta. So this whole distance is A theta. But then from that, I need to subtract the distance from P to Q. And the distance from P to Q is going to require some trigonometry. If this angle is the angle theta, then PQ is the opposite to theta in this little right triangle. So we can come down here and say this. So it's a little observation that we're going to use. That the sine of theta, looking at that little triangle, is the distance from P to Q, that's the opposite, over the hypotenuse. The opposite is the distance from P to Q, and the hypotenuse, remember, this is the radius of that circle, so that's A. And if I multiply on both sides of this equation, sine theta equals PQ over A, I find that A sine theta is the distance PQ. Does everybody see that? So X is OT minus PQ. OT is A theta, and PQ is A sine theta. So this is A theta minus A sine theta. That's X. Y, on the other hand, Y is this distance. So I need to take this distance and subtract this distance. Y, right here, this distance, is equal to this big distance. Sorry, get some pointing tools. This distance is Y from here to here, which is the same as the distance from here to here. The distance from here to here is the distance from here to here minus the distance from here to here. Distance from here to here is the adjacent to theta. So first let's write this in terms of the prescribed distances. Y is the distance from C to T minus the distance from C to Q. Do we all see that? The distance from C to T, that's the radius of the circle again. So that's A. The distance from C to Q is the adjacent in this little triangle. So I'm going to look at cos theta. I know that's the adjacent over the hypotenuse. The adjacent is the side length here, CQ, that I want. And the hypotenuse is still A. And if I multiply on both sides by A, I find that A times the cos of theta is equal to the distance CQ. Hammy, be good. Sorry, my dog chewing on himself. So coming back here, the length Y is the length CT minus the length CQ. CT is the radius of the circle, so that's just A. And CQ is A cos theta. So I come back there and I replace CQ by A cos theta. Therefore, the cycloid generated by a wheel of radius A can be parametrized in terms of the angle of rotation theta as x of theta equals a theta minus a sine theta and y of theta equals a minus a cos theta. We can factor out an a here. This is a times theta minus sine theta. And here I would get just a times 1 minus cos theta. And if the wheel is rotating at a constant speed, rotating at 1 radian per second, then I could replace theta by t. In other words, theta is a dummy variable. So if you prefer using the parameter t, we could write x of t equals a times t minus sine t, and y of t equals a times 1 minus cos t. And we can double check this by graphing these parametric curves in Desmos. But before I do that, I would like to address any questions you have about the geometry arguments here. This is not a straightforward, well, it is straightforward, but it's not a very easy derivation. I concede that. It's not super simple. It takes some work. So I'd like to know what you guys are thinking and if you have any questions about where things came from there. If not, I'm going to come back over here to Desmos. Oh, where was it? Cannot see shit. Desmos. And I will input those parametric equations. So for x, we have to pick a number for a. Let's just let a be 1. For I'll put in 2. How about 2? That way you'll be able to see what it does. T minus sine t. And then for my y coordinate, I will have 2 times 1 minus cos t. And if I let t run from 0 to pi, we get just this first little bit of the arc of the cycloid. Remember, pi is halfway around the circle. So this is what would happen as your wheel rotates. Here, let me. Y minus 1 squared. Y minus 2 squared. So here's my wheel as it starts off. And you can imagine that I'm tracking this point down here. As my wheel starts to rotate, that point, my wheel rotates a little bit forwards. That point is going to slowly start to come up. And if I look half of a rotation later, where are we going to be? That's a theta, so this is going to be 2 pi. We'll be here. And this point will have moved to this point. And as that wheel continues to rotate, we'll get this. That's 1 full rotation. And then this, 2 full rotations, and so on. And so that's your cycloid. So next time you see a cyclist on the road at night, watch his reflectors on his wheel, right? You know, even if they don't have lights, they all have those little reflectors on the wheel. Watch those. If you watch the path that those things take, it will be a cycloid. Very cool stuff, and also very important in physics when you're studying projectile motion, all sorts of different little things. Turns out to be related to the Battista-Crone problem, which is Italian for same time problem, which is another thing that 3 Blue 1 Brown has a great video on that you might enjoy as you learn about this stuff. I think that's all we have time for today, and these are kind of the last classic or really important examples that I wanted to show you guys, those families of spirals, ellipses, and then of course the cycloid. Next time we'll look at a couple problems from the homework, whatever you guys would like. It is open to you now. I'm sorry that it wasn't done. My problem with the hand, so you've got to please get back on that so we can get it fixed. Everybody should be able to look in Canvas gradebook, see their score, be able to see my notes and my comments so they know exactly where everything came from. And if you have any questions or issues or anything that doesn't appear as it should be, or especially if I reached out to you with a question, please get back to me as soon as you can, okay?
Hey, sir.
Hey, yeah, Antoine, what's up?
Okay, did you already post the exam notes?
Yeah, so I think you emailed me saying that you had some problems submitting your free response work. And I said, if I replied to your previous email, then you were okay, that I received your work. But when I went digging through my collection of stuff looking for it, I couldn't find it anywhere, nor could I find the email where you sent it. Do you still have those scanned?
Yeah, I have another scan. I think I sent to you through email, and then last time I saw the assignment for exam 3. When you click on exam 3, I submitted through the assignment too. So I don't know.
Oh, very weird. So while I've got you here just for a second, let me download those submissions again and see if they didn't show up. Maybe they didn't show up because I downloaded them too early. But you did it under here. Well, it's funny because I was looking in the speed grader too. Could I ask you to just email me those one more time? Just send them to me one more time, please.
Okay.
All right, I am rechecking the submissions in Canvas. It looks like they're here, or at least they're not showing the way I would expect them to. So if you could just send those to me one more time, I would appreciate that.
Okay, and then the second thing, so you do about the exam 4, so do you know the date?
Yeah, I'm going to give you exam 4. It's going to be a take-home. I'm going to give it to you next Thursday, the 23rd, and then it will be
Next Thursday?
Final, which is the 30th.
You said
Yep, so it'll be
20 or
you'll have 1 week to work on it.
hello?
Hello?
Yeah, so which date?
I will give it to you on April 23rd, and it will be
23rd.
April 40th.
So we have 2 exams now, so exam 4 and then the final exam.
Correct.
Okay, so the final exam is 24.
The final exam is on the 30th.
30?
30th.
30, okay, and then exam 4 is 23rd.
Yeah, the exam 4 is a take-home, so it's going to be like a project, something you'll do at home, not online. I'll give it to you on the 23rd, and you'll hand it in no later than the day of the final, the 30th.
Okay, thank you.
Cool. Okay, and yeah, just resend those scans for me if you can, because I don't see them here.
Okay, I'm going to send to you now.
Excellent. Thank you so much.
You're welcome, sir. Yeah.
Thank you. And then there was one other person I think who I was hoping to be able to talk to about this stuff today. Who is that? Israel. Is Israel here? Mute Antoine. No Israel. Okay, that's all right. I'll send him another email. So thank you guys very much, and I will see you all tomorrow afternoon.